Welcome to this webinar, The Role of Additive Manufacturing in E-Mobility and Electrification, and good afternoon to everybody. My name is Johanna Valio and I work in Yrityssalo. And this webinar is arranged as part of the growth from the Electrification Business Ecosystem project that we are carrying out together with Turku Science Park. And we are operating at the moment. We have a new brand that is called eFlow Hub, and we are trying with this brand to present the fact that our mission is to connect people and organizations and build a network and a knowledge center of expertise within this battery technology and e-mobility field. And we are also trying to look into new business opportunities and new development, what is going on in this field. And this is also why this webinar today is arranged. And I want to thank the presenters in advance for giving the presentations and also for helping out in arranging this webinar and giving advice and introducing us new people, and also my colleagues and many people in the audience too that have been positively within these arrangements. Before we start the presentations, I go through some practical issues. So first of all, I kindly ask you to keep your microphones muted during the presentations. And your questions and comments are very welcome. Please use the chat to propose them, and it helps if you address the presenter by the name, so it's easier to pick the right questions there. And just to note that this webinar will be recorded, and the most important advice is that enjoy the presentations. And now we are ready to go to the first session of this webinar, and I will give word to my colleague Linda Fröberg-Niemi from Turku Science Park, who will be moderating this first part of the webinar. So please, Linda, the floor is yours.
Thank you, Johanna. And you already introduced me so well, so I don't need to say that much about me anymore. But it was, I want to highlight the importance of Yrityssalo and Turku Science Park to collaborate around the electrification in our region, and that we also collaborate with Bridgetech in Pori-Harjavalta. And through that collaboration, we can reach actors within the whole battery value chain. And the team for today's webinar, Additive Manufacturing, we see that you actors will play a role in this value chain in the future also. There will be market niches also for these kind of competencies. And that's one reason why we have brought you together here for a webinar, and also for the audience behind the screens to give a glimpse on what's going on in this field at the moment. And the first session will start with a presentation with the title, The Role of Additive Manufacturing, 3D Printing in E-Mobility and Electrification. And that will be given by Mr. Olli Nyrhilä from EOS Finland. And Olli is the General Manager at EOS Finland and also a second positioned Technical Director at EOS Metal Materials. Please go ahead, Olli. It will be interesting to hear your presentation.
Thank you. So I hope that I can somehow keep the promise of an interesting presentation. So the double title is that throughout the history I've got used to having both local role and also a global role. So the local role is that I'm functionally responsible of the EOS Finnish subsidiary located in Turku, and the global role is that we are we have established a business unit out of the metal materials discipline, so to say, inside the EOS, and it's called EOS Metal Materials. It consists of the Finnish unit plus one person in the headquarters. So that's the reason. So I will try to handle, of course, as per usual, we have to talk about the company also, and in my case, I want to talk about two companies, because you talk about the corporation EOS and also the EOS Metal Materials business unit. But then I have kind of looked for some through some examples, a little bit of what is from my point of view important for the electrical applications in the field of additive manufacturing, and let's say this is a very not very advanced area yet, so that it's perhaps not very representative, but I hope it's useful for the audience. So first of all, this is the corporate slide, and it's not the intention to take a look on the beautiful pictures there. They are just the EOS group management at the moment. So we experienced a small revolution just over a year ago, where a lot of the old executive directors were kind of replaced by new ones, and the new CEO is the daughter of the founder, Hans Lange, Marie Lange, and together with this change, also she brought in new kind of roles in the organization, and also new people. And you can see part of them. The left side, the text is probably the more important thing, and it's EOS is still a family-owned business founded in '89, and it's located close to Munich in Germany, and the EOS is perhaps known to manufacture printers, but that's not the full story. The intention is to offer something which can be called a solution, which contains of different kind of items, of course the printers, but also the materials, and what is the most important thing, at least from my point of view, is the process, which is parameterization or software, if you will, which makes the printers work in a way that the parts coming out of the machine have some use within our customers. That's the most important thing, because it's a big investment, and if you invest in something, you expect that you get a business out of your investment, and our job is more or less to be able to make sure that this happens. Okay, this is mission vision statement. EOS's mission is to be the leading or one of the leading providers of additive manufacturing solutions, and our systems and services are essential to the digital factories of the future. So it's a part of digitalization story, a very natural part of it, and the vision is that the additive manufacturing is a key technology for advanced industrial production. So we are not interested in the garage printers or even low-level industrial printers. We want to be in the manufacturing of globally around the world. So that's kind of the little bit the figures. One way of describing the importance of a company is to talk about installed base, and that's only one number. It's not a very good number, but it is a number. So throughout the history, EOS has installed close to 4,000 systems around the globe, and out of which a little bit more than half is metal systems, and a little less is polymer systems, and this is of course shows the trend also globally that well, because polymer systems were introduced first, and the most part of the history they were always dominating, but then you know, by the introduction of industrial or high-level materials which could be used in demanding applications, that this made a turn in the distribution of the system. So nowadays metals is the kind of little bit dominating the action. Sales numbers, we experienced a relatively tough situation, you know, a year ago, which is an impact coming from slight stagnation in the additive manufacturing industry, plus of course the pandemic which hit us. We lost a lot, basically 1/3 of the sales last year. So, which of course means that the company has been under restructuring, and to some extent still is restructuring, but now it looks already much better, and they are promising, so we will survive. Okay, so now the second company, this is what we call EOS Metal Materials. It's located in Turku, in Finland, and the quite close to the so-called high-tech area, or actually adjacent to the high-tech area in Turku. And what do? We develop metal materials and processes for EOS customers, and we support the customers whenever material know-how, metallurgical or analytical competencies on metal powders, processes, and material properties are needed. So we don't only sell powders, we also provide help in terms of joint projects, or even kind of consultancy. Consultancy is not really a nice word in this context, but we want to help, and we can help our customers very often, almost always. So the history, why do we exist? Why does a Bavarian family-owned company have a subsidiary in Turku, Finland? So there's historical reasons to that, and the reason is that we started jointly with EOS to develop the all metal application for additive manufacturing, which was at that time called rapid prototyping. And all the metal materials know-how that EOS have basically comes from this organization. And the 90s, we kept on developing the technology jointly, but then 2000, because the original owner, which was Swedish Electrolux, decided that this is definitely not the core business of them, to sell the factory that the development was happening in. And then, you know, before the sales, EOS wanted to arrange a different condition for the developers, and they founded a company in Finland where all the developers moved to. And that's when we became part of EOS. So we have worked the whole history around the technology, first as joint project or collaboration partner, and then from 2000 on a part of the EOS organization. So we are now about 65 people, kind of little less, I would say, little less at the moment than half is within the R&D organization, which was the original function. But now we have also sourcing and many, like it has all the parts of a company, a normal company, except sales. We utilize the corporation sales channels. Okay, so it's a competence center for metal. So we develop the metal powder products. We have what we call manufacturing. So we have a broad product portfolio, and we don't, at the moment at least, we don't have our own powder making technology, because it would be not a kind of, or it would have been earlier on at least a kind of risky investment, because we need a lot of different technologies to be able to serve all our customers with the appropriate powder materials. So we source all the materials from our partners, which are all over the world. Then we develop the process, which is, as I said before, it is a software product which kind of makes the machine work in a way that the powder is converted into solid metal materials with known properties and reproducible properties. That is one of the key elements what is needed in industrialization, that you don't have Monday parts and Tuesday parts, but you have parts, the same parts coming out of the machines all the time. So we have a good lab. We also have medical product competence because of our history, and we have also a special group of people who do customized materials and process projects together with companies who want this kind of service. We also, because we operate globally, we deliver our materials globally, we also have to have regulatory affairs and compliance in place, so that nobody buying our products will face any authority issues in their countries, respective countries. That's a picture of our product portfolio. I'm not going to go through these things, but it's I would say the usual thing, because we were in the forefront of creating this kind of portfolio for the metal powder bed fusion metal applications, and all competition has kind of similar portfolio. That's because of our project portfolio, 15 or 20 years ago. So today, of course, the topic is mostly about aluminum and copper alloys. We have a lot of machines, obviously, for internal use. We have the big machines, and we have the medium-sized machines, and we have small machines, and they all are used for different purposes, but mostly to develop new processes and new powder materials, and also for the quality control of our powder products, because we make sure that our original promise of part performance happens throughout the history of each powder product. Okay. AM of metals is not only the printer and powder put in, it is very much about nowadays about monitoring of the process, what happens there, and in the future this probably will lead into closed loop control also of the machines. But we want to create data which confirms to the customers that everything in my job was okay, that I can rely on my parts, and they don't necessarily have to produce kind of test parts for destructive testing per each job. But they can also rely on digital data to make sure that the other parts are okay. And AM is very much AM of metal is very much about heat treatments, as metals usually is. So we have to, and we are equipped with very good setup also in heat treatment facilities. And the reason why we had to also have a know-how in this is that AM is a new way of kind of synthesizing materials, and the conventional methods around the globe, of course, are based on completely different principles, and this leads automatically to the fact that also the heat treatments which are built in heat treatment need, which is built in the metal properties, have to be also adapted for the AM world. So we have to develop new furnace processes, new heat treatments for even conventional alloys when they are brought into the AM world. Okay, so I think we are talking about electrical conductivity usually now to move on to the actual topic. So AM produces materials which are very different. So to start with, the grain size is very different from any other method in industrial use. And it enables also AM parts to perform a little bit better than the conventionally manufactured same alloy parts. So this can be used in the advantage also because design rules might be also different from this point of view. And also heat treatments are, as I talked about earlier, heat treatments are necessary, but they are also necessary for the electrical properties of conductivity. And of course, when alloying the materials, it usually improves mechanical properties, but it also then makes a conductivity less, worse, basically. And the one special notion to the antenna applications, of course, again, because AM enables relatively easy creation of parts consisting of different type of material, in the sense that you can build lower density, combine lower density and higher density sections in one part using one material, or even lattice structures. And in the surface conductivity applications, of course, then you would then make fully dense part only where it is absolutely needed from the conductivity point of view. And also space applications, of course, where weight is poison. Of course, this can help also to optimize the parts for that purpose from that point of view as well. A little bit of the specialty, a small portion of material science, perhaps, if you will. So, because of the way AM materials are created, they usually or always have a special kind of grain structure, which leads to anisotropicity also in conductivity, and also we can get rid of this also with heat treatments, like for example this aluminum part, where heat treatment has removed a structure that we saw in the previous slide, and again electrical properties are almost uniform at all directions in this after this treatment. Little bit of measurement evidence for the same story. Normal aluminum, silicon, tin, magnesium part conductivity as they come out of the machine, and then when they have experienced some kind of heat treatment. So it can be a normal stress relieving heat treatment or more specific aluminum heat treatment. Okay. Copper is a relatively hot topic at the moment because of certain interest kind of raised from different areas of the industry, and also this has led into interest of copper, pure copper, but also copper alloys. And at the same time, it has led into also at our place to make sure that we are talking about the right numbers, even in the case of conductivity. So we we standardized our way of measuring all these things and try to apply this also with all our partners to make sure that we talk about the same thing. There's a lot of things which influence the measurement of conductivity. It's geometry, surface finish, and also typical accuracy considerations and measurement method. And therefore, it can be a really confusing world because people claim certain things which are not really comparable. So usually in AM and in at least in our world, we talk about IACS, which is a comparison against historical value of fully sound copper, pure copper. Nowadays, pure copper has 102% conductivity because also the manufacturing methods of pure copper samples or parts has improved. So the 100-year-old method has also this kind of nice phenomenon. But as you can see in this scale, comparing stainless steels and pure iron into aluminum, which already starts to be a conduction material, and towards copper, the variation is big, although all these materials are conductive materials. So the challenges. There's a lot of challenges when processing copper in the AM machines. One of the challenges is that because of the high conductivity, the heat can build up in specific areas and escape completely in the other areas, which can lead into very difficult or sometimes even impossible control of the process. And you can see there's a copper platform with some test parts on top of it. Some of them have been peeled off completely, although the same process parameters have been applied to all these parts simply because of the differences in conditions on different parts of the build platform. So that's a development kind of challenge to make this work uniformly in all machines and all situations, having all different kinds of parts on the platform. Also, the melt pool size of copper processing, although you have the so-called nominal laser spot size, which might be 80 micrometers. And in some cases, then you draw a line, and because of the high conductivity, the line width will be multiples of this nominal thickness simply because of high conductivity. Also, copper being relatively soft material, you have to build the jobs or design the jobs in a way that no distortions happen because of the forces, inevitable forces in the build process. That has also a challenge. Also, the oxygen pickup of copper, which usually, of course, is only the surfaces, powder particle surfaces, can be significant, but usually not very, very dangerous. So that's why in our terminology, because we introduced already some years ago the TRL scales, where we try to describe the maturity of different products. Our copper products are at the moment TRL 3, which is kind of concept proof level. Usually it's very difficult for manufacturing companies to take this kind of materials in use simply because of the uncertainties here and there. But we are moving on, also, of course, in our work. So we have worked with three different copper alloys at the moment. So pure copper. And so you can see some application examples, and the productivity of pure copper in the machines is is relatively low because of the problems just described earlier. Mechanical properties, of course, pure copper are moderate. And then, of course, there's alloys, where people, by alloying, are trying to make compromises between the heat conductivity or electrical conductivity against mechanical properties. And here we see an example launcher example, so space example of copper alloy, where the conductivity is slightly less than in pure, but productivity, because again, because of the less conductivity, you can increase productivity in the machines. Also, mechanical properties are slightly better, not hugely better, but slightly better. And then further alloying on the right side leads into even more reduction in conductivity, also in this case productivity, but mechanical properties are then already much better than the previous two examples show. So commercial use is not very widely spread at the moment, but it's all kinds of coolers, heat exchangers, some electric motor applications, some nozzles which need copper properties, and also radio frequency communication, where you are trying to make everything smaller and of course improve the efficiency. Contacts, where you can combine again one of the biggest advantages of AM, which is internal kind of free form cooling channels. So you can drive high currents through contacts because you can cool them at the same time very efficiently. And also all kinds of inductors, because of the added freedom of design in these things. Also, this is picking up. It's just an example of additive drives, a traction motor part, which is of course a very difficult part to manufacture, but the combination of fast prototyping to serial manufacturing or small series manufacturing of these parts it's a very efficient way of introducing the traditional prototyping approach also to electrical motors. That's the launcher application. It was done in a special machine which was made by AMCM, which is a sister company of EOS. They typically modify EOS machines to be adapted for a certain application. In this case, one M400 single field machine was converted into able to handle 1 meter tall part. So this part is close to 1 meter tall, and our job in this case was to develop the process, copper chromium zirconium process, using this machine, and also enabling this part to be then built in series Cs that the customer needs. A little bit more about the copper nickel silicon chromium cooler. So certain advantages also when it comes to welding of these parts. Another example also showing some simulation of the heat distribution of a conventional part against AM designed parts, and you can see differences. And also a little bit about the future, because we have just opened the field towards electrical conductivity and also heat conduction, and we think this will be a big thing in the future. So we also want to move on by introducing high purity aluminum. You can see the properties there, and then because not all applications can handle, the kind of mechanical requirements in some of the applications, typically satellite applications, are such that the high conductivity material mechanical properties are not enough. So we want to introduce also a low alloyed version of aluminum, proprietary aluminum, which would stand a little bit forces, but still maintain a reasonable IACS values for conduction purposes. In this case, electrical conduction purposes. So waveguides, thermal management of components, electronics, casing, etc. We will see what happens. Okay, that was my introduction to our understanding of what AM and electrification might be.
We will hear about additive manufacturing in the automotive industry, about the past, the present, and future possibilities and challenges. And the presentation will be given by Jukka Pakkanen, and he is the development manager of additive manufacturing at Salon MetalElektro. Please go ahead, Jukka.
Thank you very much. My plan for this webinar is to give you some kind of review about additive manufacturing and automotive industry, because not all of us is really deeply connected to the AM, what happens every year and others. So I have been working with additive manufacturing directly since 2014, and here's my short review for the past decade and the history of the additive manufacturing in the point of view for additive automotive industry. So first of all, I want to introduce the Salon MetalElektro, and it's a part of Salon SME Electro Group, which consists of two companies. Salon MetalElektro, that is a mechanical subcontracting company, and Sorva Electro, that is doing electronics subcontracting. This company is also a family-owned, fully Finnish company, and we have been in the different businesses since 50 years this year, and the additive manufacturing was added to this portfolio in the previous years. We work with metals, polymers, and composites. So within the Salon MetalElektro Group, SME Electro Group, we can give you a unique value proposition where you have the additive manufacturing expertise, mechanical manufacturing expertise, and electronics manufacturing expertise. I think this might be quite unique within Finland and also within the whole world. So ending for the short business overview, but let's go for the review and what interests us in the additive manufacturing. So first of all, let's start what is additive manufacturing. Of course, you have heard this several times, but we can start that additive manufacturing is a method of manufacture. It has 7 sub areas that is defined in the ASTM by ASTM F42 standardization body for the different methods like wet photopolymerization, material jetting, material extrusion, binder jetting, powder bed, sheet lamination, direct energy deposition. So what you should remember from the part, it's that there is different methods. With different methods you can make different materials like metallic materials, polymeric materials, ceramic materials, composite materials. And within this manufacturing family, you might be able to find a solution that can give you good parts instead of casting or instead of metal injection molding. You might find it within the additive manufacturing families from the different family trees. So going for the short history of the additive manufacturing. Currently, it is over 5 decades of additive manufacturing. In my personal opinion, I started from the 1980s, and I say that it's the founding decade when the computational computers came. You would be able to have the first watt photopolymerization machinery, and you could find the first pioneers going. The 1990s, I would say that it's the decade of exploration. You will find to have finally like the first CAD models. You could make the computational design, then you have the computer and try to find a way how to make it make the 3D printing additive manufacturing. And a nice thing what the previous presentation Olli Nyrhilä said, that they have been here in Finland with since the early starts with metals and sometimes polymers. And here in Varsinais-Suomi, we have a good historical expertise through them and the other companies like Ajatec. And when going to the 2000s, I call that the decade of technical feasibility. More computers, more technology, more materials, metals, polymers, and also the first polymeric patents started expiring. So there became the 3D printing boom in the late 2000s. 2010s I call that the decade towards maturity. The last decade we were having a lot of good research and development and push towards the applications, and more was able to use the additive manufacturing. And from now on, the 5th decade that started, I could say that it's the decade towards utilization. Why? Let's go into the next slide and go back to the previous hype. This Gartner hype curve was from the 2012, where the 3D printing appeared into the hype curve on the top of the hype. We had material extrusion printers, a lot of plastics, metal was on the hyped also, and we can say that they kind of nailed it when they said within 5 to 10 years there will be a good utilization, and that's about now. But do you see the metal utilization, polymeric utilization? Kind of. Maybe we are still 1 or 2 years, but we are getting there. So where did we see the value in the early decade? The workhorse of the additive manufacturing had been in prototyping. It's because prototypes are expensive to make. It is labor intensive, and you need experienced personnel. And so we saw that the business value was in the prototyping, then going to the spare part production, digital warehouse, and these special parts. And I kind of see that it's going towards that way. But let's go for the last forecasts. So this is from last year's, and it says that we start from 2020, where the automotive industry could utilize additive manufacturing. So here we are seeing that they are expecting to have like 5 times the growth from the 2020 level within 10 years. And where do we see the value coming is in the parts manufacturers, in the AM service providers, We can see that one that big companies like BMW, Daimler, Volkswagen, Oerlikon and others have been purchasing and putting a lot of money into the machinery itself. Then you see the auto production and even usage of the additive manufacturing parts in automotive in the complex assemblies. So let's go for the last of the hype curve. When you remember the 2012 hype curve, this is from the 2018, so a few years ago, and we see that this is purely for 3D printing. So here we have the 3D printing in automotive forecasted to be ready in the plateau of productivity within 2 to 5 years. So when it was 2 years ago, it means 3 years have passed. So we are quite there. So we should think about this. Why additive manufacturing have been going for the automotive industry and other industries? So for the rapid prototyping, just general benefits like harnessing the impossible. Impossible because with casting you can do one thing, with machining you can do another thing, with additive manufacturing you can do a little bit everything, but it's different but still similar enough that you can use the final product. So in bullet points you can with additive manufacturing it's possible to save time from idea to object. You have the CAD model that somebody imagined, drawn. You get it printed, you get it in the hand. You can make fast adaptations. There is no need of a skilled artisan to make it. You can save material, for example, in the life cycle cost. You can utilize the different design constraints, add new features, remove manufacturing steps that have assembly labor, and make more robust part in the end. Then, of course, improved automation. You have a computer, you have a machine, it works 24/7. You need an operator instead of needing the operator to manufacture the final part in the end. Then improving quality by automation, less human factor, and when the process works well, you can just see that the process have worked. So you need less qualification for the parts when you have the process in control. I could imagine this in the same kind of leap in quality in training and operations as in the warfare was, that when you had highly skilled marksmen and then you went into the militia as a general personnel. Take a specialist out, put the general personnel, automation, saving costs and time. So this is how I imagine it, the automotive industry possibilities. Automotive industry is so huge, there is a lot of possibilities. You have really one-off models, high-end. Then you have on the opposite scale, you have the tooling, parts, and the mass production. So one-off models, if you are thinking of the prototypes that people are making, customization, then you have motor sports for the safety development, high-end models, low-run models, luxury. So in my opinion, in the top end, the additive manufacturing have been able to penetrate there. In the lower end, when going for the high production models, mass products, additive manufacturing cost-wise is not there yet, but eventually it will be able to be pushed there by the sheer mass of the market. And other where it is additive manufacturing is used is in tooling and parts. You need a small jig made fast, make a CAD out of it, print it, use it, most likely it works. So yeah, like I mentioned earlier, why prototyping started everything and why it was the financial mill to make this all possible. Because in automotive, there are different prototypes. You have a visual prototype, you have a functional prototype, you have a several development cycles, and everything requires skilled labor, time-consuming manufacturing, and they are one-off parts. And how to remove this small gap in the middle, bridge an access towards CAD to final production, this has been a huge step. Let's go for the different kind of prototypes. Like you might know, in automotive modeling, you have skilled artisans that are making visual products modeling. You have a clay models that is good to have the car small shape, also the big shape cars. You have a dolly in the bottom, then you have the frame, and you have a clay one size full car there that is modeled all the time. With additive manufacturing, maybe they can make a few steps less and cheaper. Then in the other hand, you have the older style, but I personally like a wood modeling. Like Fiat 500 was modeled fully by wood, and one by one, it is a beautiful piece of art. And of course, when you go for the components, before everything, you need to have a working prototype. You can have one-off component that you make, you test, and you finally finalize your product into the assembly line. In the old time, when Ford Motor Company wanted to have a successor for the Model T, they were doing a lot of research to be able to make a flat V6 motor fully castable, and that drained so much effort from the company that they almost went busted. But luckily they were able to make the cast block of the engine, and that one created a huge success for the next decades. So this is where additive manufacturing might help. On the left hand, you have the McLaren PX1 prototype that was that have been made, tested, and in a test track they crashed it, and it set the whole development back for a few years. So additive manufacturing can make these cycles faster. When you have all of the data, you know how to reproduce the parts, even if it's expensive, but you can reproduce it. So other thing is that there is a lot of things that we don't see in the cars. There is a lot of tooling, testing, jigs that is specially made for everything. So it is necessary to have some kind of method like additive manufacturing to make these specialized parts. Here on the right, there are some parts that Volkswagen Group is using. And going forward, then you have other conditions like safety for motorsports. You can create shapes that it might not be possible, but save life. Here's a frame up that is in NASCARs, and it saves lives when you have a roll hoop around your helmet when there is a huge crash. Going further for the industry cases, like I said, it's in the high-end automotive parts are currently leading the field. So you have like the brake parts, you have parts that are going for the limited models, 500 cars or less per the whole process. 1 million euro car and hypercars. This is the current state of the art, that additive manufacturing is able to produce parts for that one, but hopefully in the future it will be able to push itself towards the production cars. But just like, for example, Mini this year announced that they had some 3D printed decals that you could buy to Mini. They discontinued this. The market might not be there, but still it needs to be explored. Other thing is to recreate classic cars with old parts. Renault has said that they are doing it. New cars are made, and then you can, for example, reproduce old parts with the modern technologies, and you will be able to have a modern customized modern reproduction part, just like on the right for the cylinder block. In the other cases, tooling manufacture, just like the Volkswagen has been quite a lot in the news, saying that they are using within the industry the manufacturing tools made with 3D printing, plastics, saving money through there, and their head has said like using the additive manufacturing in the high-end cars currently, but maybe coming into the normal production cars a little bit later. On the left, you will be able to read the links, what different manufacturers are using additive manufacturing. Those are interesting to read. Those are from last year from 3D printing media. You should definitely, maybe if you have interest, go further into cases when you get the slides. In the automotive industry standardization, there are forwards going with ISO ASTM standardization efforts towards the automotive manufacturing and additive manufacturing field. So this is coming. It might not be 1 or 2 years, but within 5 years, definitely there will be standardization, how to make something. What about the future? Like we think about electricity, e-mobility and everything. I see that this future is like in batteries. You have a conventional design that it's an assembly. Maybe, in my opinion, in here is like additive manufacturing can be thought that when everything is made well, we could create everything in the battery in the same step instead of assemblies, saving time, money, space, and maybe we can use special materials that can create something nice. I think here is the hype, that making from the existing materials in one step something smaller. And what about the factory of the future? It will be conventional machining, it will be additive manufacturing, it will be a hybrid, more what we will have. And thank you for the listening of my small presentation review. Here is my contact information. If you have ideas, thoughts, or manufacturing needs, you can contact me and we can discuss further.
We are ready to continue, so welcome back to this webinar, the role of additive manufacturing in e-mobility and electrification. We are about to start a session 2 where we are digging into especially in the magnetic materials, and the next presentation will be given by Mrs. Lena Thorsson, who is a co-founder and AM specialist at Exmet AB, and her topic is scaling up amorphous metals for electric vehicle parts using AM. Please, Lena, you're welcome.
Well, thank you, Johanna. Is my presentation visible?
Yes, it is.
Oh, very good. Just checking. Well, thank you for the opportunity to be here today and joining this webinar of yours, where I will talk about our amorphous metals that we at Exmet are focused on. This presentation of ours wants to try to answer these questions, the what's and the whys. What is amorphous to start with? That's not a generally known topic, I believe. So don't feel bad about that. And I will start that by talking about what happens when an alloy solidifies very quickly, just as the previous speakers today have discussed. That is a natural part of AM processes. So what is amorphous? Why would we use it, and why is it interesting for EV parts? And what can we, from Exmet, offer in this? How are you using AM to solve some of the problems in this? Being a material scientist myself, I've learned that if you have a metallic melt and you solidify it, the atoms will arrange themselves into grains. There will be grain boundaries, and you, in the end, will have a polycrystalline microstructure with certain properties. And there is this certain order, a long-range order, where you have the crystals and the total structure. But what happens if you solidify the same or a melt very, very, very quickly? Well, then there isn't time enough for the atoms to order themselves, to arrange themselves into grains and grains at all. And what you will end up with is actually a frozen liquid, more or less. We can define it as that. And that microstructure is then called amorphous. This is totally normal for many polymers. It's also common or a normal thing when we talk about ceramics. We have the china we eat from, that's a crystalline ceramic material, while the glass we are drinking of is a amorphous ceramic material. And this whole phenomena and difference between the crystalline and amorphous material can also be applied to metals. And being a material scientist again, I'm interested in what solidification rate is needed to achieve this amorphous structure. And it can be described looking at a temperature and time diagram like this one, where we can see, as any common material in the normal crystalline world talk about, we have crystallization noses, where the crystallization starts and the crystallization is finished as a function of temperature and time. And the solidification rate that is sufficient to create amorphous material is at such a quick rate that ahead of the crystallization noses. And what happens then? I talked about that there are no grains and grain boundaries anymore in this frozen liquid. And yes, the material ends up with a mixture of properties that is rather unique. Looking at the mechanical properties, because it's easy to understand, we have a combination high strength and high elasticity. So high strength as of a metal, but elasticity that's more comparable to polymers, many polymers. In this webinar, I believe the ferromagnetic properties are the most interesting ones, so therefore they are highlighted on this page. If we have a ferromagnetic amorphous alloy, we have compared to the crystalline equivalent, we get a lower hysteresis, lower corrosivity compared to the crystalline equivalent. We have a high permeability, moderate saturation, a good high frequency behavior, high resistivity, and also the high mechanical strength. And what does that mean if we were to use these amorphous metal components in, for instance, mechanical structures? Well, these higher, better mechanical properties would often, if we design for it, and lead to that we can use less material, and therefore we save weight. We have lighter parts. In electrical motors and other such applications. We can increase the efficiency due to the soft magnetic properties that are excellent compared to some crystalline equivalents. And in this game, we come in from Exmet side, not being, and I will not present in the rest of my presentation, I'm not a specialist on these applications as such. It's our customers that know their applications. We offer material processes facilitating this. So amorphous metals have been known since the 1960s, but achieving these very high, quick cooling rates have been proved to be quite difficult. Using these conventional techniques such as sputtering, thin films, melt spinning, which you end up in ribbons. You can use thermal spray to produce surface coatings. The largest cross sections that have been produced with these conventional methods are measured in micrometers or possibly millimeters. So even though these materials have interesting physical properties that can be useful in applications, it has been limited. The application has been limited due to these dimensional requirements. So how the key to solve here is how to achieve these high cooling rates for larger dimensions. Well, how about just building a thin layer at a time, followed by another thin layer at a time? If that was possible, then one could imagine building complex components of any size, right? And as it happens, these very, very high solidification rates are inherently naturally there in the laser and EBM-based metal AM processes. So it appears to be a perfect match to use alloys that are actually intended for fast cooling in AM processes. It's a win-win that these materials, these components, cannot be created with conventional materials, with conventional methods, and likewise, it's a good fit for the processes where we have the high cooling rates. So that's what Exmet have been doing for some years now. Our first generation materials, we started with a slightly simpler thing and well-known alloy group of zirconium-based alloys. And that's a well-known family of alloys in the amorphous world. And here I show it today to say that this is where we have proven we got the first feasibility results from this alloy group, even though it's not very interesting for the webinar today. This is our more mature materials, and they are now commercially available through Heraeus, our licensee. Our second generation materials are iron-based, which is a more demanding material for us to process, but has also even more difficult to process for using the conventional amorphous manufacturing methods. So here we have, with these parts that we have all built here in our lab in Stockholm, we can build centimeters. The largest part here, which was built until I ran out of powder, literally, is 60 millimeters in diameter and some 50 millimeters tall. And these are alloys that we previously could just be processed to a few millimeters size. Here are a few. Then what properties do these materials then get? If we're looking in detail and try to understand the atomics, atomic world, as in a the crystalline material to the left has a higher density than ours. A normal steel has densities around 7.8, and our amorphous iron-based alloys will have a densities of about 7.4, 7.6, which can be explained by this less ordered packing of atoms. It's not as well structured, it's more random, and not as many big and small atoms. The dark blue and the orange circles can be fit in a certain volume. The magnetic permeability, here I have a small animation, can also, for those interested in those properties, be better understood as the individual atoms can react to a magnetic field in a different way than parts in a than what atoms in a grain structure can do. Oops, it goes fast. Teams. Here is the corrosivity. Typical for amorphous metals is that we have a more narrow eye in this in this M versus B field graph. And I won't talk more about that, but anyone interested in magnetics understand this better than me. Resistivity. Here we have an interesting situation, though, when we are building large cross sections as we do in AM. Normally, stacking, for instance, electrical steel sheets and laminating them, we can take care of eddy current effects, eddy current losses by this lamination, which limits these losses. This is a challenge when we come and build everything as a bulk, as we do in AM. We cannot laminate our particles in this manufacturing process. So we have a bulk instead, and the eddy current behavior is different. But here then, I'll try to summarize on this page the pros of using AM for manufacturing soft magnetic amorphous alloys. We have the material properties as we've discussed already, and the opportunity of building more complex and larger parts. We also have the design opportunities with AM, which will be used then also by a clever designer to solve these problems of the eddy current losses in bulk. This graph here, which has eddy current loss on the vertical axis, tries to show that while the bulk, the first picture of a design of the 6 designs to the right, points at the blue curves in the eddy current loss. That's what happens if you measure on the bulk. But by using these various different geometries to break up this bulk and still build using structures that are very useful and buildable by AM, you can, by just design, change the eddy current loss, lower the eddy current loss to what the second arrow points at the bottom of the graph. Then, of course, when it comes to electric vehicles, it's about identifying those printable components that are good targets for using these methods. And other people than me have, of course, disassembled cars and identified parts. And typically it comes down to those components in motors and converters that could be very good objects for soft magnetic components. So how can we explain to our customers and end users what the value of our technology is? Well, we've done a life cycle cost example for electric motor part. That's not really that, it's not the same as for electrical vehicle would be, of course, as these motors run 24/7 for years in many cases. But just pointing at the general picture, that with the current technologies that are mature and well spread around the world, material costs are very low, manufacturing is very low, we cannot compete with that, but the in-service losses can be rather substantial compared to what this amorphous soft magnetic properties could offer. AM is today rather expensive technology way to manufacture things. The materials, as soon as you go to gas atomized metal powders, you have a rather expensive material, but calculating and finding the break even when these in-service losses are so much lower, can still be an interesting business over the years. And as previous speakers have talked about, the industrialization of metal AM is ongoing, and one can look forward to that costs for material and equipment will go down in the near future, and therefore this calculation in this graph will look better in some time from now. For electrical vehicle, these lower losses and lower vehicle weights, if we talk about the soft magnetic versus also the mechanical properties and opportunities that this material offer, this translates to longer range or higher capacity and such data. So who are we, Exmet AB in brief? We are then a small SME located in Stockholm. We have was able to file patent applications, so we have paper on that we are inventor of this proprietary technology, and we can build amorphous metals using additive manufacturing. Yes, in that business we offer metal powders, processes, knowledge, alloys, and we are happy to talk to anyone interested in our materials. So in conclusion, we understand that AM for many conventional materials that has been optimized for slow processes for decades, AM then results in using AM results in rather unconventional microstructures due to the fast cooling, where we are actually torturing these alloys. Therefore, it's an interesting case to work with alloys that are actually intended and tailored for these fast processes. We also have the need in the world to scale up the dimensions of amorphous metal components. So we to explore the opportunities that lies beyond making micrometers and millimeters size samples. And by applying AM on these amorphous metals, we then get these functional materials with interesting properties for various mechanic and magnetic applications. And because we have created a functional material that is very difficult to achieve in conventional manufacturing routes. So that's what I wanted to present today. Thank you very much.
And next speaker is research scientist Mr. Joni Reijonen from VTT, and his topic is additive manufacturing of magnetic materials and 3D REMAG and SOMA projects. Go ahead, Joni.
Thank you, Johanna, for having me and the introduction. Now you should be seeing my slides. I'll just make you present remote still.
Yes.
Yes. So my topic somewhat continues what Lena presented in the previous one. So on the additive manufacturing of magnetic materials, I will begin with the soft magnetics as in the previous presentation. There was also mainly the focus, and then I will also briefly talk about the hard magnetic materials. So in other words, permanent magnets. Briefly about me, I studied mechanical engineering, so I'm not a materials scientist, so bear with me, I will not go into the level of atoms. I did my master's thesis in 2017. That was about recycling related topics in metal additive manufacturing, and since then I've been working at VTT on the advanced manufacturing technologies research group on mainly on topics related to metal additive manufacturing. Briefly about VTT, so it's a technical research center of Finland. We are owned by the government, by the Ministry of Economic Affairs and Employment, and we have roughly 2,000 employees, most of which are based in Espoo, and the second and third biggest locations are in Tampere and in Oulu. So I'm based in Espoo. Here we have the let's say the additive manufacturing lab, and then many things I'll be showing here today. Also, we work closely with the powder manufacturing lab, or the powder piloting lab, which is then located physically in Tampere. Here I have let's say a general slide, general topics related to additive manufacturing research that we do at VTT in our group. So let's say the basis of our operations is that we have quite extensive experimental facilities all the way from the powder manufacturing, so from gas atomization or plasma sphericization, in case for AM powders when you need spherical particles. We do have some other powder synthesizing means also, but these are the main ones for AM related topics. Then to the powder characterization, then the additive manufacturing labs. Here I have the laser powder bed fusion system, but now lately we've also installed a binder jetting system, but that will not be the focus of today. And then all the way to the post-processing, as mentioned already today, the heat treatments are an integral part of additive manufacturing, and then all the way to the material and component testing. And then if you think about the fields in which we do research, some are related to the applications, on new applications, such as Jukka mentioned, the digital spare parts. We had a couple of big projects on that topic in the past years. Then on the production side, it could be related to quality topics, and also on how to integrate additive manufacturing into the processing facility, since it is just a one tool in making components. Many times you need other processes of surface finishing and heat treatments and so forth. And then today we talk about let's say on the material services, and more specifically on the work we have been doing on magnetic materials. Briefly about magnetic materials. So here is a graph of two quite important properties for magnetic materials, which are the coercivity on the x-axis, and then the magnetization on the y-axis. And for hard magnetic materials, you want a high coercivity, meaning that it is hard to demagnetize the material, whereas for soft magnetic materials, you want a low coercivity, meaning that it is easy to magnetize and also demagnetize the material. So the soft magnetic materials mainly convey a magnetic field, whereas the hard magnets or the permanent magnets, as you know from your fridge door, they hold their magnetic field within the material. Few words about the applications. Where the magnetic materials are used. So generators, motors, transformers are, let's say, the biggest sectors, especially motors. If you think about permanent magnets, roughly 70% of all the permanent magnets are used in all types of motors. This, of course, doesn't mean only motors for an e-mobility. This is also industrial motors that are used in factories and in all kinds of places. And then, of course, one big section is many type of, let's say, consumer electronics, and there especially things related to magnetic recording and voice coils, and applications related to sound amplification. And here's an example of an application in the e-drive industry. So this is the motor of a Model 3 Tesla, where you can see it's an interior like an permanent magnet motor, where the magnets are embedded in the rotor core, which is, so the core would be a soft magnetic material, and then you have the hard magnetic material, the permanent magnets embedded inside this, and then you have the copper windings. So in terms of materials, if you think the motor of an e-drive, the key materials are the soft magnetic material, whichever it will be, iron silicon or iron cobalt, or even one day the amorphous metals as shown in the previous presentation, and then the permanent magnets, typically neodymium iron boron magnets, and then the copper in the windings. I tried to briefly check how much research there has been in all published on additive manufacturing and magnetic materials. And as you can see, it's quite a young but growing research field. So the first papers within these terms I was able to find from 2013. The first projects we had at VTT on this topic were started on 2015. And well, on the right hand side, you see that the whole research for additive manufacturing in general has been exponentially growing since the, let's say, the 2030s and 40s, which was around the time that Jukka showed the peak of the hype for 3D printing. But then in my topic, there was a mention of two projects, one called SOMA, the other 3D Rimac. So these are the two projects in which we currently mainly work on these topics, the SOMA on the soft magnetic materials and 3D Rimac on the rare earth based permanent magnet materials and the additive manufacturing of those. So just as a background, as I've already mentioned and came obvious in the previous presentation, there are many type of magnetic materials, and one of the key properties is the coercivity. And if you want to a really low coercivity, then as you can see, the amorphous alloys are the, let's say, the best option. But then on the other hand, if you need a maximum saturation magnetization for the material, then there are other materials on that end. So it's a compromise, and always depends on the application, which is the material then that you choose, which is the most important of the magnetic properties that you want to maximize. Today I will be talking about the iron cobalt alloys, which are on the high end of the saturation magnetization. And then why do you want to use additive manufacturing for those? So today, how these soft magnetic rotors and stator cores are manufactured are typically by laminating, using laminated sheets, which are stacked together, and then the shape is cut or stamped from the sheet. So there's a lot of waste material in the manufacturing process. Or then the other option is using conventional powder metallurgy ways, in which you are then limited in shapes, or at least you need an expensive mold for each shape. So the motivation is the same as using additive manufacturing for any other material typically, which is making complex geometrical shapes in near net shape, meaning that you don't have a lot of manufacturing waste like in subtractive manufacturing. So the first work we did with the iron cobalt, also alloyed with vanadium in as a minor alloying element, we were able to reach really, let's say, comparable properties, mechanical and magnetic, for the compared to the laminated, so the standard material that you use today. Here you can see some of the key properties, but the challenge that remained was the eddy current losses that also were mentioned earlier in the previous presentation, that this lamination is applied in the conventional manufacturing to prevent the eddy current losses. And this we don't have in additive manufacturing, which is a challenge that we've tried to tackle and try to tackle in this SOMA project also. But some of the first things we tried was, again, as also was shown in the approach by other research groups, is that we use the geometry of the component, so the clever design to introduce gaps into the material to prevent the progress of the eddy currents. Here you can see then the printed samples. So we made this kind of bar and ring samples using laser powder bed fusion, and we made the same things in like a bulky solid, and then in the having these holes in the material to prevent the progression of the eddy currents. And here you can see the results for the losses. So here, first of all, you can see that we were able to reduce the losses from the solid ring samples, and then but we weren't able to reach quite the level of the laminated structure. Sorry, I seem to have my automatic slide timing going on, but I try to manage. And then on the left-hand side, you can see the coercivity and the remanence. So the red one here, so a narrow loop here would be the ideal. So this is the conventional material. Then here on the sorry, I will do it like this. Here on the blue, you can see the printed material without, so the solid printed material without the holes. So not what we want. Then with the holes, we were able to reduce the coercivity quite significantly. We had 2 hole sizes. There wasn't a big difference within this. And the dashed line is the printed material without heat treatment at all, which was to say bad enough so that it doesn't even fit the scale here. So the coercivity was really high due to the fact that you have a lot of grain boundaries in the material, as Olli was showing in the first presentation, which is inherent to the laser powder bed fusion process. But with heat treatment, you can improve the properties, and with the design, so making a clever design, you can further improve. But we are still not quite there as with the conventional material. And then the other topic we've been then studying related to how to realize an optimal structure then for the soft magnetic cores is the topology optimization for this. So this, if you're not familiar, is an algorithm-based way of designing where you distribute material in places where you need it. So either you have material as here in the black, or then an empty space here in white. And this is quite common today already for mechanical applications. So you try to minimize the weight of the component by maximizing the stiffness. But here we've applied the same approach into a problem of designing electrical machines where the objective function is to, in this case, was to maximize the torque while minimizing the rotor mass. And here you can see because of symmetry, we used a small section of the rotor, and then here you can see the end result of the optimization. So black would be a solid material and white would be empty space. And then here is another example of a slightly different approach to the topology optimization problem, using an example of a permanent magnet motor. Again, we utilize the symmetry, so 1/4 of the rotor segment is within the optimization. And here the idea was to actually apply like a mechanical topology optimization to reduce the mass without compromising the magnetic properties. So the yellow section here was the area in which we allowed the algorithm to remove material, and this part, which is responsible mainly for the magnetic properties, was out of the optimization scope. And here you can see the result that the algorithm presents, that these are essentially areas where you don't need material, you could avoid it. And here you can see some of these, let's say, intermediate areas which are not black or white, so the border is not defined. This is due to the fact that here we haven't used the penalization in the algorithm, meaning that it enforces either open or closed. So density 1 or 0, here you can have an intermediate also. In the previous example, we had the penalization also in the algorithm. So then you get this kind of clean results, usable, so to speak, or manufacturable. And as I mentioned, now we have an EIT raw materials funded project called SOMA, where we have a lot of other companies also involved in the further development of these magnetic materials for additive manufacturing applications, where the focus is to further develop the processing of the alloy and to, well, eventually introduce hopefully to the market the powder that can be used to make soft magnetic components using laser powder bed fusion. And then the other is to explore the new designs in which ways we can also mitigate the eddy current losses, because well, both are ways towards reducing the losses. So you can either modify the alloy and the processing conditions, or then you can modify the design. But well, our approach is to do both and try to reach even better properties that we have gotten so far. Yes, and here's let's say a value chain of the processes that are involved in the project, and also the partners. So our idea is quite similar as I showed in the beginning for what is, let's say, the core competence of our research as VTT, is that we can cover the whole chain from the powder manufacturing all the way to the end of testing the performance of the components. And of course, here we also have partners. We are not doing it alone, but this is the, let's say, the philosophy behind the project. Then I will switch to the additive manufacturing of hard magnetic materials or permanent magnets, the 3D Rimac project. And here we have slightly different properties that we are targeting. So for a permanent magnet, the main property that you want can be summarized as a maximum energy product, the BEH max, which is basically a combination of high coercivity and high remanence magnetization. And as you can see from this graph, the best properties can be achieved with the rare earth based alloys. So previously it was the samarium cobalt alloys, but then since the early 80s, the neodymium iron boron alloy was discovered, and that has basically since then dominated the market because of the superior properties that you can reach. And again, you have the same motivation. Why do we want to use additive manufacturing to manufacture permanent magnets? Is to make complex shapes without waste, and here especially minimizing the waste is of key importance, because neodymium, one of the main components here, it's also they are typically also alloyed with dysprosium to some extent, and also terbium, which are all critical raw materials, mainly controlled by the resources are over 90% controlled by China. So these are really strategic materials for the EU, and therefore if we can reduce the waste of, so when we manufacture magnets out of this material, if we can do it with least waste, that is of course the target. One other way, so So there are two ways to make these magnets today. One is to sinter them from powders, press and sinter. And then if you need a intricate shape, then you need slicing and cutting, which will then generate waste. And then the other way is to use polymer bonded injection molded magnets, where then of course when you have the polymer matrix, that will reduce the properties, the magnetic properties, and then again you are limited by the expensive mold if you want to make many different types of shapes. Here is the earliest work, which was not done by us. This was by another research group. The results were published in 2017 about the first case of using laser powder bed fusion to process neodymium iron boron like fully dense, so without a polymer bond, and to get some meaningful properties out of it. So a coercivity of roughly 800 kiloamperes per meter and 0.655 Teslas roughly for the remanence magnetization. These are quite good, but still they are not in the level of the high-end sintered magnets that you can make conventionally. Here I have some properties for two different grades, whether you want high coercivity or high remanence, because at some point it's a compromise again. You cannot have both in the same. But since then, it has become evident that actually using the alloy that they used, and we've also used in other research groups, the specific powder for making these magnets, this is the maximum you can get out of this alloy by using laser powder bed fusion to process it. So to go further, we need an alloy which is tailored for the conditions of this process, which are highly different from the conventional sintering, or actually as this powder that was used in this example is a powder that was intended originally for the bonded magnets. But the challenge is that to get the high properties, you need a specific microstructure. And actually here, what you want, the best mixture is where the sintering process is tailored to do. So what you want is equiaxed grains which are surrounded by an neodymium-rich grain boundary phase. And if you remember from, for example, from Olli's presentation, the microstructure that you get after laser powder bed fusion, it's totally different, and this is not optimal for this material. So this is one challenge. So how we can create a structure where each of the grains are surrounded by this, so to speak, insulating neodymium-rich grain boundary phase. And then the other challenge is that there isn't a powder commercially available that would have the proper powder particle size and shape. So we need spherical particles instead of this type of irregular shape that are used for the conventional sintering of these alloys today. And the same goes for the particle size distribution. So in sintering you use a lot smaller particle size, and what we need to do is to shift the peak into an area which is usable for the laser powder bed fusion process, meaning that it is so easily flowable, and you can spread the powder in homogeneous way so that the process works. And the purpose of our project is to make such a powder which is spherical, which has the proper particle size distribution for the additive manufacturing process, and which also has a alloy composition in which we can reach the desired microstructure and the desired properties then in the end. And then there are some other challenges, but I will not focus on those. So this is also a project that is funded by the EIT Raw Materials, and there's also quite many partners involved in the project. This is has been running already. So the SOMA project started in the beginning of this year. This project started last year and will continue this year also. And the target again here is to as the limiting factor of using additive manufacturing to make neodymium iron boron magnets is that we don't have a suitable raw material, a suitable powder to do it. So the main target in this project is for us, together with our partners here, to develop such a powder that works in the process, and you can get good magnetic properties in the end for the parts. So here you can see the again, let's say the value chain or the processing chain. So here again we have the partners that are involved. We are able to cover the whole chain from the casting of the alloy into making the powder. Here we use actually the plasma spheroidization to make. First we use jet milling, then we spheroidize the particles to make them round and suitable for the laser powder bed fusion. Then again, a heat treatment will play a crucial role in reaching the desired microstructure and hence the desired properties in the end for the parts. And then we also aim to make some demonstrator components to show in which type of applications you could utilize the 3D printed magnets. Here on the right hand side you can see let's say the current status. So as I mentioned, it's an ongoing project. Unfortunately, I cannot yet share with you the final results because we don't have them. But what we have so far is that we have the powder, let's say, ready, so to speak, that we have been able to make spherical powder, and also the particle size distribution is suitable. Here in this image, this is an earlier version. You see quite a lot of really small particles, which are bad for the flowability. But now we have further developed it, and in the newest version of the powder, we have been able to get rid of these fines. So it's much more flowable now. But anyways, even with this powder, we were able to print some components that you can see on this image. Some first magnets, and what we are then doing now, and which is the main focus of this year, is to further modify the alloy, so with minor alloy additions, and also optimize the heat treatment profile to get the desired properties of high coercivity and high remanence. But I'm running out of time, so I just have a few things to summarize. So in the end, what is our vision is that by combining, as I mentioned, the whole chain of designing the components, the electromagnetic components, designing the material, the printing process, and all the way to the application. Because if you can make a lighter weight motor, for example, for an electrical drive, that it's just one part of the drivetrain, and if you are able to or let's say make more efficient motor, then you might be able to have less battery weight, or so to speak, a longer range, which one you would then choose. But anyways, in all steps of these, you can reduce the amount of these critical raw materials that you use in electrical e-drive application, and which are crucial for these, because without these materials, you cannot reach the properties that you want. But on the same time, these materials are of high, let's say, controversy, in a sense that their availability, also price, are quite volatile. So just to conclude quickly, there's a solid foundation for using additive manufacturing in both hard and soft magnetic materials, but it's quite obvious that further research is still needed to meet those properties of the conventional materials that we have today. But I'm confident that we can reach and even in the future exceed these properties. And then to get the best out of this, you need to combine the material, the design, and also then the manufacturing process. And in each of these steps, you have significant potential to reduce the use of these critical raw materials in these electrical machines. From the end, you can find some publications we have on the topic if you are interested more on the details. Thanks.
And our next speaker is Mr. Tero Hämeenaho. He is AM lead in Etteplan, and then he's the chairman of the management board at FAME, that is Finnish Additive Manufacturing Ecosystem. And his topic is added value comes from the design, and he also tells about FAME and how that speeds up the industrialization of AM in Finland. So please, Tero, you can start your presentation.
All right.
Yes.
So shortly about myself. So my name is Tero Hämeenaho, leading the additive manufacturing and optimization development here at Etteplan, and I have a background in Etteplan 17 years now. So I have been in various positions and come from the mechanical engineering background and have been seeing different manufacturing technologies and use of those one in many different applications. And shortly about Etteplan. So we are a consultancy company focusing purely on the design. And from manufacturing aspects, the services that we are offering can be seen here. So we are heavily linked in the design of the new and current products. We are working in a different level of components, from simple AM components, plastics, to a critical components with certain customers. And we don't possess any printing capacity of our own, so we are working with the service providers, research institutions to help our customers to really get advantage from the additive manufacturing. So what we do, we help our customers to implement additive manufacturing from idea to market. Added value comes from design. So today's engineers, they are facing new challenges. So there are shorter product lead times, there are increased requirements for carbon footprint and material performances. Same time, the supply chains are changing, new demands are coming from there. And if we look at the manufacturing processes from the past hundreds years, it has been the same. We take a bunch of material and start to remove it with the different tools. And there are certain limitations for the flexibility when you are using current tools and methods on a market. And even more and more, the engineers are seeking new technologies, how to make better products for the future needs. And today we have here about where the additive manufacturing, where it has been started and where it is heading, what kind of material development there is. And I will tell more about how to get the added value out from it. So if you think about additive manufacturing in overall, so that the added value or why to use additive manufacturing comes from these bullets. So we have a lightweighting components. We can use special materials to make those lightweighting components. We can make really complex structures. We can make part consolidation to get advantage from additive manufacturing. The materials, like say today, there's a lot of development ongoing over there. In future, we can have a custom materials for certain applications. AM enables a mass customization. It helps in a logistics and spare parts in a whole on-demand manufacturing technologies. Levels in additive manufacturing when thinking about the production. So you can make the printing in a conventional way. So print the current design as it is. Or you can make small changes for the design so that it is printed easier. Typically in these cases, you are working in a spare parts or material change cases, or then you have a lead time issues that you want to tackle. But really to get the benefits from AM, it comes from the new product development. So utilizing the degrees of freedom, computational fluid dynamics, topology optimization, part consolidation. And through these ones, have the knowledge in the organization to really start to utilize additive manufacturing in a new product development. So start from the scratch, design for the function. And this will set the bar to skilled engineers. You need to use new tools, new software tools. You need to have new skill sets to be able to make those complex geometries. Take, for example, this topology software that we are using to generate the triply periodic minimal surfaces. These are extremely good in different kind of heat exchanger cases, but almost impossible to do with the current mechanical engineering tools that you have at house. This example is something that will be printed with the metal binder jetting, almost 99.9% copper. So the applications are already there. There are tools to make this design so that engineers' wild plans can be implemented to the future products. Few cases from the world. So Olli already showed this one, and this is really interesting coming from the car sector. So design for function, not just to replace the current way of doing. So replacing rectangular copper rods will replace the current wide copper rods. And it's a mindset in engineering to think that, okay, I have a new technology, how I will benefit it the best way. What kind of shapes would be better than the current one? And in this case, it's about the torque and the efficiency of the motor that you can achieve while implementing this one. Simulation-driven design comes, and there are different kinds of simulations. There's a topology optimization. You can simulate through cost. You can simulate through shape. You can simulate through build process, through fluid, through acoustics, or make antenna designs. And that's really vital, and you need to have these skill sets in your team when doing the future designs for additive manufacturing. Not just replacing the current designs with the new technology, but using the benefits that it can bring. So do different kind of concepting that normally minimize the use of material, these near net shape products. It's a function-driven design, and through design you can minimize the post-processing, the material usage, the cost of the product. Bringing new functionalities, shorter manufacturing time, no post-processing needed. Example that we have done for the copper is antenna design, and this has been simulated in our antenna laboratory in Jyväskylä. So 5G antenna made from copper, feasible already today to print these ones. But it's not only about like prototyping and testing. So with certain application and with the wise engineering, you can really find the good business cases already from additive. This is an example not coming from the car industry, but it's a really good example because this is like a dummy Y connector made for Mirka robot sanders. The annual volumes are more than 1,000 pieces in this one, and in past this part was manufactured in China, and there were a long lead time, and we started to work with this one. So what we did, we find out that this component was suitable for the shape so that we could make a nested build. So utilize the whole build chamber volume when manufacturing this one. That gave a significant cost savings when we were able to design the product to be nested. And in the meanwhile, when designing it newly, we had also other better performance and characteristics for these components. So it's more than 50% cheaper than the China-made component nowadays. But the interesting cases comes from the world. So Dinger is one company that is really taking this technology further. So they are really revolutionizing the car manufacturing at the moment and how to think about that one. So certain parts from the cars are manufactured by AM and then combining those one in the normal manufactured components. It's a hybrid manufacturing. But it's really changing the way that how the cars are made. And the same factory can change the models really fast. And if you think about that, what's the investment to build a new car manufacturing production line or factory? We're talking about hundreds of millions. So this new digital way of doing things will revolutionize the whole car making industry. And for example, PSA, the car company, is really researching this a lot and doing cooperation with this divergent company. And like Jukka said, now the cases come from the hypercars, but it's coming from the new technology. For example, BMW is using certain parts in their production where the annual volumes are more than 50,000 pieces. And there the additive manufacturing is feasible manufacturing method in the cost-wise. One other case that I wanted to show you from the world is relativity space. So they are making rockets size of mid-size. And the cool thing about this company is that this is the second largest space company now after SpaceX, still developing, getting investments. But what these guys are promising. So they have started to think about from the scratch that how the rocket could be made by 3D printing. And similar type of rocket has 100,000 parts. And they are promising to make the rocket less than 1,000 parts. Similar type of rocket has a 2 years build time. And these guys are making a rocket in 60 days. 95% of the parts are made by a printer. And they are developing the largest in-house printer so that they can print the parts of size of 10 meters or something. So new players are coming to the market who are totally thinking about different way how to make the manufacturing innovative, practical, scalable. So utilizing intelligent and robotics and data-driven manufacturing and 3D printing, and it enables and continuous optimized production. So within less than 3 or 6 months, they can bring a better rocket to the market. And they are really skyrocketing now in the field of additive manufacturing and collected some investments more into their company. But the company was founded at 2015 and the valuation is $2.3 billion at the moment. So technology, certain companies are going ahead. So shortly about Finnish Additive Manufacturing Ecosystem FAME. So why FAME did start? So additive manufacturing as a technology, it develops so fast. Companies need to fully understand the effect of additive manufacturing, and many companies have worked by themselves in the past, but it hasn't skyrocketed in Finland yet. We are missing big investments, and we don't have that big companies in Finland who would really make a big invest into additive manufacturing, that level of investment by themselves that we can see from the world. That's why we need to collaborate and start to share things. So we decided to start practically and tangibly and use the ecosystem resources to build 3D printing experience pool for the members. First, experience something small and then scale it later. And as the technology evolves so fast, it's really hard for people to understand, or people tend to overestimate the change that will occur in the next 2 years and underestimate the change that will occur in 10. People wiser than me has said this before. And what the FAME will do, we want to break the silos between the companies. Start to make co-innovation and research together and start to build the competencies around that one. Share knowledge. So shortly about the activities that are now in the FAME roadmap in total. So public and private funded R&D program, co-innovation program, where the target is to create a certain kind of material databases, share information from different additive manufacturing technologies so that all the FAME members could speed up their business and utilize the common ground of additive manufacturing knowledge that we can generate. So through these companies that are now in board, we can have big enough research projects. We can work with the research organization like VTT and universities and guide their research into the way that the Finnish industry can benefit most from additive manufacturing. So ecosystem operations include also this R&D program preparation. So the FAME or DIMAC is doing that one. We are going to launch certain kind of trainings and benchmarking tools, events and communication and promoting, of course, to help small and mid-sized companies to take advantage of additive manufacturing and build business around that one, and then participate in international cooperation through network, so that not everybody needs to be involved in those ones, but we can have a one-point contact that then spreads the information to the other companies. In the lowest low, we have AM campus ideation, so certain kind of facilities to really start to validate the AM components for the serial production. So there's a lot of service providers and universities where you can do a prototyping and testing, but really like speed up the validation and then have the recipe for the 3D printing ready. That's the main target for the additive manufacturing and the FAME. So more than 30 companies now on board. Here's a list of those companies. And this is what we do at FAME. Hopefully we can speed up the industrialization of additive manufacturing in Finland. Thank you for my behalf.
We are now moving forward and to our last presentation. And our last presentation is given by Mr. Heikki Saariluoma, and he is a senior lecturer in technology industry in Turku University of Applied Sciences and also a researcher in Turku University of Applied Sciences and Lappeenranta-Lahti University of Technology project combined in AM and EV field. So, and his topic is research and production environment for electric vehicle parts at Turku University of Applied Sciences based on the laser powder bed fusion and other laser processes. So please, Heikki, the stage is yours.
For introducing me. So I will speak now more about from more practical way about what Turku University of Applied Science and Turku region is doing in this area, and so I go to our area. So as we are an educator, it's our challenge now is to implement this still new technology to our education, and but we have good possibilities there because we have infrastructure for designing, and now also actual part making, material testing, and also serial production capabilities, and that we can actually realize the real serial production, or at least zero serial production, and so on. We have also our partners starting from Turku and University. We are working with Valment, Fraunhofer, Accurate, and just to mention someone. And Turku Machine Technology Center is located in same facilities, and you will hear more about what we can do together. Also, we have this e-rallycross car project, which is nice learning and research environment for e-mobility. So what has been done basically is a standard A-class Mercedes has been changed to e-rallycross car by the persons of Turku University of Applied Science and the students. So to the today's topic, we have now two laser powder bed fusion machines, SLM 280 with two 400 watt lasers, and at the moment they are planned to use the one machine for aluminum, titanium, and stainless steel materials, and the second one is more for cobalt chromium for the dental research and education purposes. So that's the way how we are now starting with this. And as a software, we are using Materialize Magic for build preparation and so on. So the first parts are made, and once again, our aim and challenge is to implement this to our courses and to education for the new engineers. So we have the Siemens NX environment. Actually, all software components are available for us, and we can use those for research projects and thesis works for the students, and of course in the courses for product development and similar to those, we can use the softwares, and so we should have pretty nice tools in the area. And concerning the EV field, there is also a Sim Center AMESIM simulation environment for battery systems, and this can be used also for the research project, which is actually about 1/3 of our budget is coming from the research and innovation projects. So this is available also. There are ready models, for example, this Tesla Model 3. So we can think about to change one component and see how it changed the behavior of the model, and this way we can get more information how the vehicle engine transmission or thermal integration is working. And back to AM, for the topology optimization and lattice structures, we have ANSYS software available also, as well as in Siemens Nastran and Fustrum resolvers. And for the printing process, we can use ANSYS Additive Suite and Siemens Center 3D Additive Manufacturing module. And for example, displacement can be simulated with those programs. So, as a simple example, there is an injection molding tool. In the top row, there is a conventional way build coolant fluid channels. It's typically before made by drilling or milling process, and geometry is quite limited. In this case, the maximum temperature was 180 degrees, and after the new design with the more effective and smooth coolant channels, the temperature was lowered almost half to 100 Celsius. So this kind of studies can be easily made also in the courses or as a thesis works. So in this area we can use NX advanced flow CFD calculation, for example. Okay, then when we have something ready, we are interested to know how accurate the part is. For that, we have a new 3D scanning measuring system from ZEISS. So we are able to achieve 0.04 millimeter accuracy, and for more precise pieces, there is a coordinate measuring machine available, and then we are level of 1 micron in the accuracy. So for the 3D scanner, we can use the 3D model, actual model, designed model, and compare it to the scanned result, and easily see the errors. Like in this green picture, there's some yellow, which means 0.1 millimeter difference from the model. And when there is a need testing, making the mechanical properties testing, we have a tensile test machine and impact test machine. Also for the hardness and specimen grinding, polishing equipment as well. Also we have some microscopes and surface roughness can be studied as well. So that's for the AM parts, and what other possibilities there is to when we are thinking about new assembly or or a bigger structure, there might be other techniques also what should be used. So we have sheet metal cutting, forming, bending machines, robots, and maybe more interesting is the laser welding and laser cladding possibilities. So we can even think about to make some cladding to the AM produced part, maybe. But all these are in a very small area, in new campus area in Turku, Kupittaa area. So these are available. And going deeper to the laser welding, a new optics has arrived where we can use 10 kilowatt multimode fiber laser. Then the spot size is 800 microns. And then we have another fiber laser with the single mode, and there we are able to use to get the 50 microns spot size with the fixed optics and 120 microns with the scanner. But this inline process monitoring is interesting, so we can measure during the process the height of the workpiece, seam profile, if it's changing, the wobble function in the head can handle 5 mm variation plus minus, and simultaneously we can measure the keyhole depth, which is telling how well our welding will be, and the finished surface and the transverse profile as well. So this is giving some possibilities to also weld AM produced parts. This is a field which is studied lately, and naturally, sorry, we are interested to do this more now with the new equipments, and when there is a cases, please contact. So is when we thinking about more about the EVs, and then we have capabilities also to make welding for the batteries, to join battery cells and build the modules, and finally we can think about to build a whole battery pack. At the moment we are doing already some smaller packs to our own research equipments. Also new dissimilar joints, for example copper aluminium. It's a very typical situation with batteries, so not necessarily the 1000 nanometer wavelength is the best one. So new shorter wavelengths are coming, like green and blue wavelengths, about 400 to 500 nanometers, and these studies are made currently also. So this was very short overview what we have as facilities and equipment wise at the Turku, and naturally our aim is to implement this very much to our education and as mentioned to the research project as well. So thank you very much, and if you have any questions, feel free to ask.